Welcome to next class 4. Today we will continue with the previous video, whatever we had learned, that is Josephson effect. So already we have completed this. So this Josephson effect, very in a brief way, we will state here are of two types here. Okay, so two types of Josephson here. DC Joseph effect, we call it as a Joseph DC Joseph effect. Okay, what is this Joseph effect, DC Joseph effect? So when DC current is when DC current, okay, when DC current is flown across the junction, okay, is passed, I can say, across the junction. Yesterday we have seen that, you know that what is junction. Even when no voltage is applied across it, even when no voltage is applied across it, okay, across it, so that we call it as a DC Joseph effect. Okay, so here what happens when the DC current is flung is across the is flowing across the junction, even when no voltage is applied, that we call it as a DC Josephson effect. Similarly, AC Josephson effect. Okay, so what is here? So when a DC voltage is applied, so here voltage is not applied across when no voltage is applied, but here when you apply DC voltage, this is difference. When you apply DC voltage across junction, okay, across the junction. So here radio frequency current, okay, then what happens? Radio frequency current oscillations is produced. Oscillators are produced. So this is called as AC Josephson effect. Okay, so when you apply DC voltage, so here when you don't apply DC voltage across the junction, so DC current is passed across the junction. Okay, when even when you not apply the voltage, DC current is passed through the junction. So that is called DC Joseph effect. But in AC Joseph effect, you are passing the voltage. Okay, DC voltage, when you apply a DC voltage, but here DC current is passed across the junction. Here what will happen when you apply the voltage? Here radio frequency current oscillates. Okay, oscillations are produced. Okay, oscillations are produced. So this is what about the two types of Josephson effect, that is your DC Joseph's effect and AC Joseph effect. And some regarding this, some derivation is there, so that is based on the physics related, so we don't want this all things. So yesterday one derivations we have done with the Josephson effect. Okay, so that you can keep the last equation, what we had, fourth or fifth equation, what we have represented, that equation you can keep one and state how it affect for the electric field versus current, so that you can show for the Josephson effect, and these two you can keep in mind. No need of the further derivation of these two types. Okay, next is your Hall effect. Next effect is your Hall effect. What is this Hall effect? So we will take a slab here, semiconductor slab here. Okay, so we will make it here like this. So this is slab here, and you are going to apply a battery here like this also. Okay, and you know the current will flow from positive here like this, like this, like this, like this. Okay, so this is your current is passing from positive to negative here. So what will happen now? Your electrons current is going to flow reverse of that. So this is what the current flows here like this on the opposite sides of the you can say the current, how you from positive to negative current, positive to negative current is flowing, and opposite to that the electrons are flowing here in this way. Okay, and this is a conducting slab here, conducting slab. Okay, that is your conductor, conductor. Okay, it's a conductor slab here, and these are the electrons. Okay, So this is what we will think, and here direction is very much important. Here you keep down this direction here like this and like this, okay, XYZ direction. This is very much important here. X you take it here, and this is Y and Z here, okay. So like Fleming's right hand rule is there, no? Fleming's right hand rule, something like this we show. So that Fleming's right hand rule, for example, if this X is, you are going to get a current here, okay, you are making flow the current in this direction, and this direction you apply the magnetic field. If you apply the magnetic field, what will happen? The current, so here the electrons, they flow in the opposite direction perpendicular to the magnetic field and current. This is what the Hall's effect is, okay. So this was suggested by, this effect was suggested by E.H. Hall, Professor E.H. Hall, okay, in 1897. So what he says, when a magnetic field is applied, so when a magnetic field is applied, okay, when a magnetic field is applied perpendicular to the direction of current, to the direction of current, perpendicular to the direction of current in say perpendicular direction of the current in a conductor. You can take here, it is I have shown here in a conductor, okay. In a conductor, what happens when a transverse electric field is developed, then this is important, transverse electric field is developed, transverse, TRANSVERCE, transverse electric field is developed, okay. This electric field is perpendicular to, this electric field is perpendicular, okay, this electric field is perpendicular to the direction of the current, okay, to the direction of current, to the direction of the current and magnetic field, current and magnetic field, to the direction of current and magnetic field. This phenomena of production, of transverse current, transverse electric field, transverse electric field or current, transverse electric field, okay, is called Hall effect. This is called as Hall effect, okay. And this electric field, whatever is generated, is called Hall field. This electric field, whatever generated, is called as Hall field. So here like this, okay. So when you pass the current here, okay, in X direction, and perpendicular to that, if you place a magnetic field, I will place here like this. Now if I place a B here, magnetic field vector B, okay. Now what will happen? These electrons which are flowing now in this direction, so they become now perpendicular to the this like this. Now they divert here, shift in this way, because your applied current in this way and a magnetic field in this way. Now current inside what are flowing here, electrons, they go, you take the transverse electric field, so that means they come this side perpendicular to both here, and they go and slit on the slab here like this. So this slab becomes now very negative charge like this, okay. When this slab becomes very negative, opposites will be very positive. This is a Hall effect. See here, this will become positive, see here, okay. So like this effect we call it as a Hall effect, okay. Now we have considering this slab here, okay, and we are applying as a result of potential difference here. So here the potential difference is been achieved here, okay. Potential difference, or we can call it as a Hall voltage, okay. VH, sometimes we give it as a VH, Hall's voltage is produced, okay, between these two phases. So that is what Hall's voltage we say it's, okay. Because of the achievement of this potential difference, a Hall voltage has been produced across these two phases here, okay. Now if you see what may be the application here of this, so if you see the application now, yes, Hall's effect used to determine the nature of charge carrier. It is used to determine the nature of charge carrier. It is used to determine the nature of the charge carrier. And if you take the second application, that the number of charge carriers per unit volume can be determined. Number of charge carriers per unit volume, okay, per unit volume can be determined by this Hall's effect, okay. And even it is used to measure magnetic field, used to measure magnetic field, okay. It is also used to measure magnetic field with that is a Gauss meter, with use of Gauss, GAUSS, Gauss meter, Okay, so this is it's the working is based on the Gauss meter. This working is based on the you can say Hall's effect. Okay, Gauss meter. So this is how magnetic field can be determined by this effect, that is Hall's effect. Okay, and also it is used to determine the drift velocity. Okay, Hall's effect can be used to determine the drift velocity, that is VD. Okay, it's a physics term of a charge carrier, Okay, so this is what about the Hall's effect. I think this is more than sufficient. Okay, so Hall's effect diagram is you have to draw this diagram. Okay, show the current passing here like this, and you are passing the voltage here in this way, and you can see the potential difference is developed here. Okay, across this slab here. Okay, the negative and positive, and this is what called as a voltage, Hall's voltage. Okay, so this can be used in, I have given you where this effect can be used. Okay, 3-4 applications I have given you. So this is what about the, and this is what is called transverse electric field, transverse like this. So this is what electric field is generated, transverse, that is called as a Hall effect. Okay, so this is you can add in the electric material or field of conductors, superconductors. Okay, next we will go for HT, that is your HTS, high temperature superconductors. Very important, high temperature superconductors. This is very much important. Okay, because at the most now what we have learned, superconductors are which are working with less than 20 kelvins. Okay, having the temperature less than, that's what mercury, how much it was there, 4.2 kelvin. Okay, superconduction TC, that is critical temperature, was 4.2 for mercury. Okay, so like this for even niobium, if you take the TC temperature is 9.2 somewhat kelvin. See here. So these all are low temperature super LTC. Okay, but this is very costly. Okay, this is very costly. So if you money wise you cannot afford for this, very costly, only rich countries can afford for this, but the underdeveloping countries may not go for such. But what is required now, that's why HTS. Okay, high transition, high what is temperature superconductors is okay, economic, I can say. Okay, and that's why most of today's research is bending on this, that is high temperature superconductors. Okay, now these substances are the or they these substances, actually I will state here, these substances, okay, are the superconductivity show the super which show the superconductivity, I will write here, which show the superconductivity, at temperature greater than, I said you, greater than 25 Kelvin. See, this is what greater than 25 Kelvin is called high temperature superconductors, HTS. Okay, this you have to remember, greater than 25 Kelvin, less than that low temperature. Okay, so this nowadays HTS, they represent a very new class of substance. Okay, and their properties application have now energized in every field. In the research is where now it is attracting scientists. Okay, in research it is attracting most of the scientists for for its better application and low cost, worldwide. Now the research is highlighting on this HTS. Okay, because low temperatures commonly we get it, but for high temperatures very difficult, because resistance will be more, and it will lose the conduction. But in that case we are achieving the superconductance, means a great work, and it has been now in some case we are doing it, and the research is highly attracted now in this work here. Worldwide it is becoming the famous in this work. Besides, you can see these HTS, okay, high temperature superconductors, they are usually the salts, that's why they are combined. It's not normal elements here, they are made up from the salts of rare earth elements, Okay, so they are made from the rare earth elements here. Okay, and usually in the copper oxide, this is what of made up of the copper oxide. Okay, cupric oxide, you can say, containing element. For example, there is one HTS, high temperature superoxides, that is your mercury, barium, okay, calcium, copper oxides here. Mercury, barium, calcium, Cu3O10. This is what one type of high temperature superconductor, which is oxide, and here is rare earth element combination with this one. So you can see it's having the TC value, critical 135 Kelvin. Very nice. Okay, 135 Kelvin. So that's why it is called as what you say, high temperature superconductors here. Okay, now like this you can see the very properties of this is very beautiful. Now 135 degree, the cost is very economically, we can go for this, but it's a mixture of like perovskites, we have learned peroxide property. Okay, so they are having some structure of peroxide structure type of mixture is here, so which gives the superconducting nature here. Now if you go, the what is the speciality of this superconducting high temperature is that they have high anisotropic structure. So they are having high anisotropic structure. What is this anisotropic? That means they are having different optical properties, okay, and electrical properties or magnetic properties. So they differ in this, okay, that we call it as a anisotropic structure. So this is what the first property of this HTS is, okay. And even you can see that the Hall mobility of HTS is very small, okay. The Hall mobility of HTS is very small, okay. Just now we have learned the movement of the electrons and all in Hall movement, so that mobility of this is very small, okay. And bonding of atoms is covalent in nature. Bonding is covalent in nature, not ionic here, so it is covalent in nature. The bonding of HTS is covalent in nature, and they are brittle in nature, brittle substances, okay. These HTS are brittle in nature, brittle in substances, and they can't carry large magnitude of current, okay. They cannot carry large magnitude of current, okay. This HTS, they can't carry the large magnitude of the current, and that's why we can call it as they are the type 2, okay. So they are type 2 superconductors. Type 2 means hard superconductors. They are in the category of hard superconductors, okay. So this is what we can say of the superconductors, okay. Now we can see that there are HTS, okay, HTS of the type uh, high temperature superconductors of the type of range from 170 to 200 Kelvin. This range also we are seeing, okay. Research is going on in this case, okay. And you see, yeah, and these are usually from the ceramic materials. Now we have to acid ceramic materials, okay. They are not simple combinations, so they are made up of ceramic materials, and you can see that it depends on the combination. As just I see, and some more of the HTS we can see here. High temperature, that is your lanthanum, barium, copper oxide. This is also one type of superconductors here. Lanthanum, barium, copper, HTS. In HTS it comes here, okay. And one more is there, 1, 2, 3 superconductors. They are called as 1, 2, 3 superconductors. So usually they ask in 2 marks question, that is 1, 2, 3 superconductors is nothing but yttrium, barium, copper, oxide. So 1 barium, 2 copper 3. That's why it is called as 1, 2, 3 superconductors here, okay. And this has a TC value to 90 Kelvin, okay. So that's why it is 90 Kelvin. That's why it is called as HTS, okay, high temperature superconductors, okay. So that's what. And one more just we learned, that is your mercury, okay, Hg and barium, calcium will be there, copper, and this one, okay. Just now we studied, that is mercury, barium, calcium, copper oxide, okay, superconductors. So like this, and they are I said very perovskite type of structure will be there, and it contains, like here see here why it is called as 1, 2, 3 here, because it contains 1 atom of yttrium here, okay, 2 atoms of barium, and 3 atoms of your copper is there here, okay. So that's why and yeah, 3 atoms of this is there, and that's why we call it as a 1, 2, 3 superconductors. We call it as a 1, 2, 3 superconductors this way, okay. So this is what it has been asked here, and so you have to keep at least 2, 3 names of the HTS, okay. Now lastly, if you go for application here, application of this, no, one by one. So if you see in the practical application of this electric power, so you can take one by one. Electric power, the first we can see is electric power, okay. So this is now superconducting magnets, okay. Powerful, we can, it's a powerful superconducting magnets nowadays. Powerful superconducting magnets, powerful superconducting magnets, okay, can has been transformed electric power, okay, infrastructure to a great extent. So it has been transformed the usually the electric power infrastructure, whatever the electric power now we are seeing infrastructure. So use of this has been transformed now. Superconducting materials have transformed this electric power infrastructure to a wide extent, okay. So if, this now for example superconducting winding is there, winding, okay, superconducting winding is been replaced. No, they are replaced by the traditional what we wind now. By nowadays copper and aluminum is winded. Okay, if you see any mixer or any transformer, inside that you can see the machine. So always copper and aluminum is winded. Okay, that can be replaced by superconducting winding. So this can be done. Okay, so we have to replace it. Okay, and that's why in the generators, motors and transformers, generators, motors, transformers, okay, so nowadays instead of copper and aluminum we can substitute with superconducting winding here. Okay, because it can carry a large amount of current, because this carry a large, the superconducting material can carry large amount of current. Okay, large amount of current with no energy loss, with no energy loss. This is important. Okay, but usually if what we are using copper and aluminum winding, so what will happen, they carry the large amount of current but there is heavy loss. Okay, so whenever there is grid and all, what current we are getting in our home and all, so what happens while transformation from current from the grid to our home, what will happen, most of the current is lost. Okay, if it is 100%, 60%, 40% is lost. But if you use the superconducting windings, then definitely 100% current we are going to utilize here. So that is fascinating. Okay, so current, large current it is going to carry, along with that there is no energy loss. This is the important, I can say, the application of the superconducting windings here, or use of the superconductors. Okay, once this electricity is generated, it can be distributed to long distances. Okay, with minimum loss. So we can distribute to long distances and with a minimal loss. Okay, so that's why such generators in idle projects, okay, thermal power plants. Okay, so we can use this. Okay, we can replace this copper and aluminum winding with the superconducting windings. Okay, so this is how and even the energy can be stored in this superconducting windings for a long period of time. The energy can be stored in this superconducting materials. Okay, so this is how we can see the what I say, yes, the application of this HTS. Okay, and even it will prevent the overloading from the grid. Okay, so this will prevent overloading from the grid. Okay, so usually there is overload of the in the grid here of during this saving the charges current here. But if you use the superconducting material, so this what is say, the overloading of the grid is prevented. Okay, so HTS one, I can say, that is we call it as overloading, is called as fault current limiters. Okay, we call it as a fault current limiters, LIMI. Okay, fault current limiters we say it. Okay, limiters. Okay, if you make this fault current limiters from superconducting material, so it will prevent the overloading from the grid. So like this also you can see. Okay, and even if you see this they are very, so what is the use of this, using this is because again it will give a compact in size, because of using of this will give you a compact size. Okay, if you use the superconducting material, and more reliable, compact size, more reliable, and environmental friendly. Okay, so these things is a plus point, I can say, of using this superconducting material. Okay, and next is what you are even in transportation nowadays. Transportation, what is the best use of superconducting, because transportation is what sea or road we do it. Okay, transportation which uses more large surface area, and also pollution also is there. Okay, so this is what we can minimize by using the superconducting HTS in this, and that is what nowadays we can see in transportation also. We are using this, like in Japan and all, they are using this techniques. Okay, in running this leviators train, magnetic leviators train and everything. Okay, you have seen that very fast. Okay, even in propulsion ship propulsion system. Okay, in ship, that is your in oceans and all. Okay, in ships will be there, no? So in ships also you can see that propulsion system. So they are using this type in transport, and they are using this superconducting materials. Okay, so like this we can see in transportation also it is very much used. Then we can see in communication. In communication, where we are using HTS filters, we say high temperature superconducting filters are used. Okay, so in cellular communication, so in mobile and all cellular, in cellular communication system, you can see this HTS filters has been used. Okay, so they enhance the signal to noise radio, enhance the signal to noise ratio. Okay, they enhance the signal to noise ratio. Okay, that is very much important. Okay, clarity, signal to noise ratio. So that is the specialty of this superconducting materials. Okay, so and even they enable cellular communication system to greater with few or more spaced cellular tower. So that's what, even in next is electronics. Okay, that is what chips, in preparation of computer chips in electronics. So computer chips are made up of superconducting film nowadays. Okay, very important this is. So they are more compact and much faster, more compact and much faster, more compact and much faster. Okay, so chips are nowadays superconducting films. Okay, and these chips can transfer the information very rapidly. Okay, not what silicon chips we are using normally. So if you use this superconducting chips, so it can transfer the information very rapidly, very fast transfer of the you can say the information will be there here. And even it helps in it can no, superconducting can help in electronic industry to build more powerful reliable energy. Okay, so this is what. Then in medicine, fifth you can take in medicine also. Okay, HTS provide very MRIs and all, that is magnetic resonance imaging. So they are all made up of HTS. Okay, magnetic resonance imaging. So I will write here magnetic resonance imaging, magnetic resonance imaging, MRI scan and all we do. Okay, so in that this HTS has been used. Okay, and even in MSI, what is this MSI, you know, that is magnetic source imaging, magnetic source imaging. So this also they use HTS in the medicine. Okay, for cardiology study, cardiology study. Okay, they enable actually in the diagnosis of brain, in diagnosis of brain and heart, in the diagnosis of brain and heart. So this is used. Okay, magnetic cardiologist. Okay, so it gives the signals and that can be used in study that in the medicines we can use. Okay, and next one we can take it as magnetometers, magnetometers. Okay, in this also very is there, that's we one technique. What is there? Squids, SQUIDS. What is this SQUIDS? Superconducting. Okay, superconducting quantum interference device. I will write here superconducting quantum, superconducting quantum. Okay, superconducting quantum interference interference device, interference device. Okay, so this is called a magnetometer. Okay, this is used to detect a weak magnetic field. It is used to detect weak magnetic field. Okay, used to detect the weak magnetic field as a result of current signals from the brain. Okay, current signals from brain, current signals from the brain. Okay, so this is used. Okay, so biological current we say it, which is been transfused from the brain. So biological current, so that can be detected by this magnetometer, which uses the superconducting material squids. Okay, so like this, these are some of the application part of this HT. HT. Okay, that high temperature superconductors and usually superconductors. Okay, so I think this is more than sufficient in this video. In the next video we'll go for the next here it completes, I think, superconductor. All the first this whatever in syllabus is there, how touched here. Okay, next we'll go for the conduction in ionic salts. Okay, thank you.